Hello everyone, I'm Mariusz Szczepanik. I'm bridge design engineer from SKANSKA, Poland. And during today's webinar, I will show you how to model and analyze composite steel viaduct. Okay, here we have our schedule, what we'll be discussing. First, project information, then how to create a static scheme, and how to enter material properties and time-dependent material properties, then how to create geometric characteristic of sections, then construction stages, load combination, and analysis results. Here we can see a cross section of the viaduct, and this structure, this superstructure, based on 6 steel beams, which are made of S460 steel. These steel are 1019 millimeter height, whereas they are connected with concrete slab. This slab is made of C30 by 37 concrete according to Eurocode. And on this viaduct we have standard equipment. So we have lightning pole, guards, sidewalks, protection barriers, asphalt layers, and etc. Carriageway is 7.3 meter wide, and we also have a sidewalk plus bicycle path, which is 4.5 meter. Viaducts consist of 13 spans, which are 28 and 33 meters long. And we have expansion joint on every pier, which is marked in blue color on this drawing. So finally, we have 3 independent superstructure. One is 4-span superstructure, then we have 6-span, and at the end we have also 4-span superstructure. During today's presentation, I will show you the analysis of this 6-span viaduct. Okay, and how to start? I have to say that that this viaduct has really complicated geometry. So in the top view, it is in curve. We have some skews, and also in a profile, it's also curved. So the geometry was really complicated. And in my personal opinion, when we have such a difficult bridge or viaduct, I mean geometry, the best option is to prepare the static scheme in drawing program. It can be AutoCAD, for example, or other program, other software. Save it as DXF and import it to MIDAS Civil. And now I will show you how to do it. Okay, so we have our software open. We have kilonewtons and meter. We should remember about this to enter proper values. And now we can start. So we have to push import button, then AutoCAD the XF file, browse, and we have our the XF file. We have to choose layer, and we have two possibilities. We can import only nodes, and we can nodes plus element. I will choose the second option. And we have our structure. This structure consists of one-dimensional elements, so it consists of bars which are in 3D dimension. So concrete slab is also a model as a bar element. It's not a model as a slab or something. Okay. Let's back to the presentation. Okay, so the next step which we have to do, it is establishing of boundary and boundary condition and boundary group. Okay, to establish, if you want to establish boundary, we have to use this menu. We click define supports, and we have to create boundary groups. And okay, so let's do it. We will have, in this model, we will have temporary, how to say, bearings and permanent bearings. So, okay, so we have our boundary group, and now we have to, when we enter our support condition, we have to choose, we have to prescribe to which boundary group it will belong. Now, sorry, now we have to choose the condition of boundary. Okay, and I have to say that this structure was concreted, I mean slab and cross beams, because cross beams are also made of concrete, were made in 3 phases. So the first phase was concrete from this pier from the first pier to the second pier, and 1/4 of the next span. and the second phase, it was concreting of these two spans up to 1/4 of this span, and the third and last phase was concreting these two spans. So we have to adjust our bearing condition. So firstly we blocked all, and then we also have to block against bending moments. And now we choose nodes. And we have our boundary condition, and the same we have to do with the next span. Okay, I will show you now how it looks on the completed model. So we have our boundary condition and the construction stage 1, and during the construction stage 1 we have only steel beams which were assembled on the piers. And the structure looks like this, as we can see on this model. The second stage is the concreting of the slab and cross beams. And the next stage is concreting up to this part of the bridge, and the last stage is like this. And during these stages we deactivate temporary bearing to permanent bearings, and I will show you everything of this. Okay. Okay, the next thing which we have to do is to enter material properties and time-dependent material properties, and for this purpose we can use internal MIDAS library of materials, or we can use user-defined function. Alternatively, if we want. And how to do this? We should go to the properties, to the top menu, then push the button material, properties, add, and we have a library of materials and codes. I choose Eurocode and steel as 460 N. And click apply, and we have our steel material. Because it's composite bridge, we have to choose concrete glass as well. So we choose C30 by 37 and apply, and we have our concrete. As now, as we can see, we choose property name, material name, and every element is now made of steel. It is because as a first material we've chosen steel. Here we have some concrete elements, like for example this dummy cross beams, which represents concrete slab, and also these cross beams over the piers are made of concrete, so we will have to change it. And to change material of some elements, we have to select them, and to select this material we have to use this this button, select by window, for example, and we have to, I will show several of these dummy cross beams. Close, and then we go to works, and here we have our list of materials. We choose concrete, and we use so-called drag and drop function, and we have our element changed. The same thing we can do when we have section property, which I will show later. Okay, so let's get back to the completed model. I will show you how it looks like on the completed model. So we have property, material name, apply, and every element is described, what kind of material it's made. And as we can see, the main beams are made of steel as 460, and cross beams are made of concrete. Yes, we can see this. This is C30 by 37. Only this cross beams, this extreme cross beams, are composites, so they are made of steel. Okay, so the next step. So if you want, the software calculate for us creep and shrinkage effects. We have to use creep, shrinkage, and compressive strength function in the main properties, and connect them with the proper concrete grade. And I show how to do it. So if you want software calculate for us these effects, creep and shrink, So we push properties, creep and shrinkage, add, and we have to, okay, but I will show this on this second model. So we have properties, creep and shrinkage, add. We should choose code as well. Could be ZFIB or European, because European code based on ZFIB, but I will choose European code. Name C 40 by 37. Okay, first thing to do is to enter characteristic compressive cylinder strength of concrete, and it's kilonewton per square meters, so we have 30,000. Okay, relative humidity of environment could be 70%. It's viaduct. If it would be a bridge, it should be more, about 80-90%. Notational size of the member 0.2. Notational size of member, it's the area of the cross section. In our case, it's concrete cross section. Multiplied, oh, sorry. Okay, I will save it. Because it will repeat from time to time. So notational size of member, it's, as I said, it's area of the cross section of the concrete part multiplied by 2 and divided by the perimeter. But perimeter have to be in the contact with atmosphere, and so we have this value. And we also should choose cement class. I will choose this is a normal cement, not rapid strengthening code, and we can see the result. We can have creep coefficient starting from 0 and ending to 1000 days. And we also can see shrinkage strain as well. Okay, and we have our first time-dependent property, close. Second is compression strength of concrete, compressive strength of concrete. We have to enter the name C30 by 37. Choose code, and our code is European. And we have to enter mean compressive strength of concrete plus delta F. And this delta F is given in the Euro code, concrete structures, and this delta F value is 8 Newton per square millimeter, or 8 megapascals. So we have 38,000, and we can see the result, how concrete hardening during this 28 days process. Okay, close. And now we have our time-dependent property defined, but we have to connect these properties with our concrete, which was defined by us before. So for this, we have to use this button material link. And here we have creep and shrinkage, C30, and we have compression strength. and we choose our concrete this, and we push add, and we have our time-dependent material property connected with our concrete. And now the software will take shrinkage, creep, and strength of concrete. Will take these values during the calculation, of course. Okay, close. Yes, and we go to the next step. Okay, so now we have to define our geometric characteristic of the cross section, and okay, it will be better, and we can do it in two ways. So the first way is to use internal library of section which MIDAS has, and the second option is to run the external program which is called sectional property calculator, and in this program we can create or export or import DXF file, for example, from AutoCAD, and I will show you the both way or both option to creating such a section, composite section, I mean. Okay. So we have our uncompleted model, and now we will be creating our section, composite section. So we have to, sorry for this, we have to push this button, section properties, and then add, and go to the composites. We choose still I, give the name. For example, it will be number 1. Okay, then slab, we have to enter slab width. And our slab width for prescribed to one beam is 2.17. Number of girder 1. GTC 2.17, BC width of girder 2.17, TC is thickness of the slab, and we have 2.22 meter, and this H, in our case we have 0.06 meter. Okay, and now here we have to enter the dimension of the steel sections, and we have as follow HW, so it's height of the web, and this is 1.028. B1, it's width of flange, and this is 0.4, and we have thickness of the flange 0.038, and the same for the lower. Oh, sorry, it's web. Thickness of the web 0.018. TF2 is for lower flange, and we have the same. I have to admit that this section of the steel part are rolled sections, and they were made in Luxembourg. So it was prepared in advance. After this they were transported to Poland and prepared and built up. So this section wasn't welded section. It was prepared in the steel mill. Okay, and then we have to choose materials for our composite section. And B2, which is also 0.4. Okay, so we'll select them from the database. And for concrete we have this. And for steel we choose as 460, sorry, and we push apply. Okay, and as we can see, this section was prescribed to the all elements. The software do exactly like in the material case, and we will have to change this because we have different beams. We have cross beams, dummy beams, and etc. Okay, so to create, for example, this dummy beam, we can choose the same button. We push add, and now we can choose, because dummy beam has rectangular section, we can choose this. One and user, and we have to enter height and height and width. Have 0.22 and width 1.40, and click apply, and we have our dummy. Okay, and now we have to prescribe this section to our cross beams, and we have to select the elements which we want to, this section will be prescribed. Let's say it's this element. Okay, and we use drag and drop function. Okay, and now, as you can see, we have our dummy crossbeam. So sorry for this. Here we can see exactly how it is. Okay, and the same we can do with the cross beams, because these cross beams are also made of concrete. So we have to create several cross sections in such a bridge like this, and prescribe this crossbeam to the proper elements. Okay, and the second option how to create a cross section is the sectional property calculator. And now I'm going to show how to use this option. So we have to choose from the main menu tools, and here we have sectional property calculator and run this. What is very important, we have to choose the same kilonewtons and meter, because we have in our base model. So we have to choose the identical units. Tolerance 0.001 and got step. We click apply and OK. And of course, in this sectional property calculator, we can create our section using these commands. But I think, and for me, the better option is to import it, for example, from AutoCAD. Okay, and here we have our section. What is important when we import such a DXF section, this section it shouldn't consist polylines, for example. It should be built only from lines, because if it's made of polylines, then software won't accept such a section. Okay, so we have the shape of our section. And now we have to choose materials. Okay, the first material is our steel S460, modulus of elasticity. Okay, let's go to the completed model. We can see how the values of this material parameter from the basic model. And for example, for steel, we have modulus of elasticity 2.1. Poisson ratio is 0.3, density is like this. We click apply and we have our first of our material defined. Then is concrete. And modulus of elasticity, I also can't remember this, but we can see in the main model as well. Okay. So we have to enter this. Poisson ratio 0.2 and density is 25. Maybe 26 in Polish conditions sometimes. When we have concretes which are made of basalt gravel, click apply. Okay, close. Okay, now we have to generate our section. We go to the composite section, generate, and we have to enter the name of our section. Our section consists of 2 parts, so we have to enter the number of parts. We can choose up from 2 and 3 parts. So 2 parts, and base material is a steel. And we click apply and close our parts to composite. So we have to choose this option, add to composite, and we have first material will be steel beam. Okay, we have steel beam, and we have to choose the steel part. For this we have to press control button and left mouse button, and we have to choose our parts of steel section. We have already done this. We click apply, and we have steel section generated. Now we have to add concrete part. So choose concrete. Part name is slab, can be slab. Slab. ID part is 2. Okay, we have B. And for the same way, we have to choose the concrete part. And we can choose different color and click apply. And we have our composite section. Now we have to calculate this our section. So we choose calculate composite property, and what is very important, we have to enter mesh size. It should be we have to enter the proper value, because if value will be too small, it will take us a lot of time until section will be calculated. So I think the proper value will be 1, and we have to select entire section and click apply. Section is being calculated. And we have information that new composite section beam with 2 parts was generated. Okay, let's wait. Next step will be export this section to the MIDAS, and I know how to do it. Close. As I said, now we have to export this section. To do this, we choose export composite. We have to give path name. Let's say it will be beam 2. 2. We have to save it as sec file, and we have to select our section and click apply, and we have our section exported. Close, and now we can close sectional property calculator. Yes. Okay. Now we have to open our created section here in MIDAS. So section properties, add, we have to choose composite and composite general. And now import section. And we have RBIM2, open. Okay, and we have our section, and here we can show calculation results. For example, value before composite are given and after composite. Here we have close, and we should give the name of the section. It will be composite BIM 2. Click apply, and we have our composite section. And now we can prescribe to the proper element. As we can do like this, then we choose list of elements, and then use drop and drag, for example, drag and drop. Sorry. Okay. Okay. After we enter properties, we have to create construction stages, because our bridge is built in many stages. Exactly, there are, I think, at least 4 stages, because one is assembly of steel beams, then we have three parts of concreting entire deck. So have to choose load, construction stage, and define construction stage. Add. We have to enter the name of construction stage. Let's call it construction stage number 1, and duration of this stage, because during this stage entire beams will be assembled, and let's say it will take us 15 days. We also can generate steps. So within the space we can generate, we can divide this stage into some steps. Okay, and before we generate such a construction stage, we should define element group and loads group. So apply. Okay, and here we have the menu when we can define structure group, for example. And we have to create such a structure group. So the first structure group will be steel beams and cross beams. It will be the first, and the second will be concrete cross beams, construction stage 2. And concrete construction stage 3. And construction stage 4. And we have to prescribe every element to the structure group as well. So for example, for steel beams, there will be this element and not this part in the middle, because it will be made of concrete. So I will show only for two beams, for example, because we have some time limitation, and we use drag and drop function, and the same we can do for the cross beam elements. And I will show on the completed model how it looks like. We have our completed model here. And for example, for the construction stage, for the first construction stage, we have only this steel element, yes? We have only the steel elements, and they are working as a steel without concrete slab. And for the third part, we have partially, we have part of our structure works as a composite section, and the next part as a steel section. And the next construction stage, construction stage 5, we have other part of our structure which works as composite, and for the 6 we have entire part. Okay, so let's get back to our uncompleted model and define construction stage. Modify, and now we have to activate in every construction stage. We have to activate our element, and it will be steel beams and cross beams, and this element will be active also in the next stages until we deactivate them. And okay, it will be all the elements. Boundary, we have to also active boundaries, boundary group, and it will be temporary bearing, which we created before, temporary bearing, and loads, and we have to create them. Okay. So now I will show how to enter loads. So first we have to choose static load and then element load. We have to enter load groups, and these load groups will be necessary to activate them in construction stages. So first we have to we have steel beams, and then we have concrete slab, and then we have equipment, by the equipment I understand, for example, asphalt layers, sidewalks, barriers, insulation, and things like this. Okay, and we can also define here another type of loads, but now I will show you how to define this dead loads. Okay, now we have to define this our load cases with steel beams. And what is important, we have to choose the type of loads, because when we choose dead loads, this load will be take into consideration during construction stages, and all time-dependent effects will be calculated together with these loads. So it is very important to choose in the proper way this type of loads. Okay, so we have dead loads and add. Then we have concrete slab. For example, it's also the dead load, and the third will be equipment. We can choose this dead load of component or dead load of wiring, surfaces, and utilities. It also will be treated as a dead load. Equipment and close. Now we have to choose load case names, steel beams, and load group names, as well as steel beams. We have to enter value of the load. This steel beams weight over 300 kilograms, so it will be 3.4 kilonewtons. And we have to choose the elements for which we want to prescribe this load. And we should choose every steel element. So I will show only for 2 or 3 beams, because it would take us a lot of time if I choose every beam. And we click apply, and we can see, oh sorry, because it should be minus. If we make such a mistake, then don't worry. You can choose load tables. Load tables we have here, and we choose static load and beam load. And here we have every load we defined before, and in this table we can choose our value on minus. So we don't have to worry when we such a mistake. We can copy this value, copy and paste. And we have now proper value of our node to the end. Okay, because here we also have positive value of our load, but we can change it as well. Using copy paste. Oh, and now we can see that our load acts in proper direction. Okay, the same we do with concrete slab. Okay, but it will be minus. We'll check it in Excel. It will be minus 19. Depends which beam it is. Minus 19. But we have to also choose proper load group name. And we also choose our element and prescribe the load. Okay. And we click apply, and we have our concrete load. And then go back to the construction stages. Construction stage, define. Here we can modify construction stage, modify, and we have loads, and we choose steel beams because in the first construction stage only steel beams load will act. Okay. Of course, when we define dead load, we can use the function which so-called self-weight, which will calculate us the self-weight of construction. It will take from the size of cross-section, but I prefer to do it, to calculate it by myself. I'm more confident of such a way of doing. Okay. When we defined, I will show you as well how to define moving load. This load will be defined according to Polish norm, not Eurocodes. We have Eurocodes in Poland, but we are obliged to apply our Polish norm when we calculate or when we enter the loads. So we have so-called heavy vehicle. This name is K vehicle, and here we have a scheme of this vehicle. It's 4 axles, 8 wheels, and weight of our vehicle class 8 is the heaviest vehicle, is 800 kilonewtons. We also calculate so-called dynamic factors. So as I said, we have 4 axles, wheel space is 2.7 meters, and axles are every 1.2 meter. So now I will show how to create such a vehicle in MIDAS. Okay, so to define the moving load with our code, there is no Polish standards here. So for me, the most convenient is to choose ESTO standards, because I can define my heavy vehicle in easiest way. So the next step is to choose vehicles. I will choose user defined, and here we have truck lane load. And as I show you on the drawing how this vehicle looks like, it's 200 kilonewtons per axle, and axle spacing is 1.2 meter. And we click Add and have first axle defined, second, third, fourth. And I have to enter vehicle name. It will be heavy vehicle K, and we click apply, and we have our heavy vehicle defined. Close. The next step is to define traffic lane lines, so I also show you how to do it. So click this, and we have to choose the name. Let's say it will be lane 1 or number 1. Eccentricity. It is the value value of offset of the vehicle. For example, when we choose extreme beam, the center of the heavy vehicle will be offset for such a value. So I will give 1.86. Wheel spacing is 2.7 for our vehicle. 2.7. Impact factor, it is dynamic factor. We can give it or not. It depends of us. Usually I don't enter here this dynamic factor because I add it later on during the design, which I may make usually in Excel. So I will leave it as 0. And also important thing is to vehicular load distribution. And okay, and we have to choose on what kind of element this load will be distributed. And so we can establish. We should have established before some cross beams as a structure group and choose it. Okay, let's say it will be concrete cross beams, and we have to choose our lane. So we start from here, and so sometimes when we have a curved bridge like here, we can't jump over several elements. We have to choose every element. So it can take some time. So I won't show the entire process of creating here this lane, but only on 2 spans. Okay, so we click, then we can click apply. So we have such a line, so let's call it lane 2. Okay. So we have our line created, so close, and now we have to enter moving load cases. So we have to join our lane or lanes, because we can have more than one lane with the vehicle or vehicles which we created. moving load cases, add load case name. So let's say it lane number 1. We have here scale factors when we have more than, for example, 2 vehicles. It depends on our design codes, what to write here. According to Polish codes, there can be only 1 heavy vehicle on the bridge. Okay, so add, choose lane 1, and now we have connected the lane number 1 with our heavy vehicle K. Push OK and apply. And we have 1 moving load case. Okay, and now I will show you some results on the completed model. Okay, we have a very nice function in the MIDAS, which is called, it is in the result, moving load tracer. We can see, for example, what is position of our vehicle or vehicles for the moment in choosing element, or for the displacement in one node, for example. So let's say we want to have a displacement, and we want to know what is vehicle position for the node 172. So the node number is 172, and we are interested of FZ, and we also have to know the value. Okay, let's do it once again. Displacement 1.72. Okay, so let's see the result. For example, moments. Okay, now we can see moment due to our heavy vehicle. Okay, we have the moment and graphs of moments, pending moments, and we have value given. If you want to select, for example, a particular beam, beam in the middle or extreme beam, we can select and use filters. For example, let's say that we want to see the result for this extreme beam. So we can choose them, select the elements. Okay. And active. And we have results only for this for this beam. And we can also rotate the values of the forces, and we can have our moment envelope. Okay, so let's back to this moving load tracer. I will active entire structure now. Okay, moving load tracer, displacement, and we have our node number 172. We want to know what is position of the heavy vehicle for DZ value, and apply. Okay, and we have now, you can see the position of the heavy vehicle. We can see the value of the load, 100 kilonewtons per one wheel, and we have 8 wheels. And here we have value of the displacement for such a position of the truck. And the same we can do also for, let's close it. We can do this for bending moments, for example, reinforced moment, and then we have to choose the element number. Let's say it will be 322. It will be, we can choose the position on the element, so it can be in the middle of the element. And now we also have position of our vehicle, and we have the value of moment, bending moment. So it's a really nice thing, really nice feature of MIDAS. And okay, and we can also see the stress value, and for a moment I will show how it is. So we can choose stress beam diagram, and we have to choose for which load case we want to have our stress diagram. So let's say it will be from the moving load. And what is important, we have to choose the part of the section. It will be for the first part and the lower part of the section. And we also can change the units, Newton per millimeters, values, and apply. And you can see we have a graph of stresses. Okay, it will be more convenient to rotate the value output. But what is also important in MIDAS, that we have tension as a plus and compression as a minus, and you have to remember about this when you got the stress results. And we also can see the stress results for part 2. This is a concrete slab, and for the upper part of the slab, and we have our value for the slab. Okay, and load combination. After making calculation, we can enter our load combination. It's here in the top menu. We have to choose the name. So let's say it will be combination number 1, active, and we should choose type of combination. Should it be add or envelope? Let's say it will be, we choose add, and load case name. And for example, I can choose Q load, which is live load, and Q load is spread over the layer surface. And here we can choose as well factor, which increase the load. For example, 1.5, 1.5, and Q6, 1.5, and close. And now we can have a diagram from this load combination. As you can see, it's combination 1. Apply, and we can have we have our stresses value, which comes from this load combination. Okay, and we can also see the stresses and bending moment in which comes during construction stages, but it will be from the long-term loads. So long-term loads. By long-term loads, I mean dead loads and equipment loads, for example. Let's say face. And we have, it is in the first construction stage, and only steel beams are working, and this is steel section, not composite. And we have the value of our we have a value of stresses due to self-weight of steel structure and weight of concrete in the upper part, and we can have in the lower part, for example. In lower part we have 165 Newton per millimeter or megapascals. It is the same. And for the next construction stage number 3, and when we have summation value, it will be stresses due to dead load and creep and shrinkage effects. So we have to remember about this, but we can have only due to, for example, shrinkage and due to creep only. Okay. And I think it's everything for today. Thank you very much for attention, and I hope we will meet again. Thank you.